So initially, when humanity started working with electricity and that, we came up with a way to turn things on and off using electricity, and that was to use a device like this guy here, which is a relay. This is an electromechanical device. We put basically a small electromagnet, and then there's a little metal bar that moves up and down. So if we put power on the electromagnet, the middle bar moves up towards the electromagnet, either turning on or off. And so we could do electrical switching, but there's some limitations to these guys. They only switch, and they can only go so fast. Maybe a really good one could turn on and off maybe 100 times in a second, which seems fast for a person, but not very fast for anything electrical. So those problems were overcome by the invention of this device right here. This is a vacuum tube. And the vacuum tube solved a whole lot of electrical problems in the sense that it can switch on and off really, really quickly. It can turn on and off hundreds of thousands of, if not millions of times in a second. And it could also do something that the relay couldn't do, in that I can take a small signal, put it on the grid of this thing, controls a much larger signal, so it can amplify in the same way the transistor does. But these have their own problems. They still have a limitation to how fast they can go. And there's inside of here, there's a filament that heats up that's needed to operate the vacuum tube, and that can burn out, just like a light bulb. They kind of figured these out from light bulbs. So they're hot, they burn out, and they're not very fast. So in comes, and this is a fairly small vacuum tube, so they take up a fair bit of space as well. Then came the transistor, right there, which we looked at before. And the transistor has a lot of advantages over the vacuum tube. It's smaller, requires less power, doesn't heat up as much, doesn't require heat to operate, and can operate way, way faster. This cheap little transistor can probably turn on and off 250 million times a second, no problem. So, great, transistors. So let's look at a circuit with transistors in it, right here. So this is a circuit that can, amongst other things, be hooked up in such a way to cause a little light to turn on and off. There's 26 transistors there, and by changing how we hook it up, we can have a light blink on and off, or we can have a light blink on and then stay on until something happens, or stay off until something happens, or change its state. So it's quite a versatile little circuit, but it's still fairly large. So back in the 60s, these guys were invented. This is an integrated circuit. This tiny little chip has all of this on it. It has these 26 transistors. All these resistors are all on this tiny little chip. And in fact, if I take the power off of here, just turn it off for a second and disconnect this guy. Let's get him out of the way. I can put this guy back in place of it. If I line everything up right. Back in place of it. Turn the power back on. And we have our blinking light again. So all of this is on there. And that's where integrated circuits are really good, because they take up a lot of what would take up a lot of space and make it very, very small. And in some ways it makes it a lot easier to do a lot of electronic stuff, because now most of the work's already done for you. The circuit's all in there. We just have to put some support hardware out there to tell it what we want to do. The trick now is to read the data sheets to find out which of these pins does what, and then have it make our circuit.
Okay, so looking at what we just, the actual schematic set from what we just were looking at, this here, big thing on the left, is the schematic for the discrete transistor timer. And it's got a whole bunch of transistors and resistors and so on and so forth. And the nice thing about using integrated circuits is all of that is on this one little chip right here. So when we're drawing schematics and all that, we can abstract all of this down into a single little package like that. And you don't need to know what all of this in here is. All you need to know is what all these pinouts do. Like, so what these things do, that's all we need to know. We don't need to know that there's, some transistors here or what and all that. So integrated circuits in some ways simplify our design and use of electronics somewhat. So how do we work out what pin does what and what all those pins do? Well, that's where the data sheet comes in. So here we have the data sheet for the little timer. It's a 555 timer, and there's various types of it up here. And here we have the package. And there's a couple of packages. This is a different type of package, does the same job, but we don't need to worry about that right now. We're just looking at this one right here, which is the DIP package, or dual inline pins. So we got 8 pins. And if we come down here, it tells we have the pin numbers right here. And then over here we have what they do. So for example, pin 1, here it says GND, that's the ground. So that's our minus power. And then pin 2 says trig, which is trigger, and so on and so forth. So the data sheet, when you're using ICs, is very important because it helps you figure out what each thing does and how to hook it up. Another thing that this little diagram shows here is the pin numbering scheme. So we have a little notch, and when you've got that little notch going up, to the left of it is pin 1. And then the pins are numbered going up like that. So 1, 2, 3, 4, and then they go across, and then they come up like that, 5, 6, 7, 8. Sometimes there isn't a little notch, there's just a little dot, and the little dot is also pin 1. Now the thing to look out for when you're using schematics and all that for integrated circuits is the pin numbers on the schematic aren't necessarily in the same order as the pin numbers on the chip. So this first pin here, which on the chip is pin 1, it's actually pin 2, and the schematic will label what number the pin is. So pin 2, so this here, TR, is this over here, this trigger pin. Pin 1, our ground, right here, is actually down here. Okay, so this line connects to here. Okay, not down over here somewhere. So it's kind of important to pay attention to all the little numbers that show which pins these are. Okay, so pin 7 is pin 7. Pin 8 up here is pin 8 over here. Okay, so when you're reading from a schematic over to the actual integrated circuit, remember to check to make sure the pin numbers are the pins you're using.
Now, the circuit we looked at earlier was an analog circuit, so it was based on varying voltages and so on and so forth that cause things to happen. This is a digital circuit, and basically things are either on or off. So right now we have 2 inputs, which could be on or off if I push the buttons, and an output, which is right now it's on. And this particular gate, made up of these 3 transistors, is a NAND gate, or not AND. So as long as both these aren't on at the same time, the light over here will be on. If I put them both on at the same time, the light comes off. But if only one of them or none of them are on, it'll be on. This is a common gate because you can use it to make a bunch of all the other gates. And as you can see with transistors, it takes up at least 3. So they do make these in integrated circuit form. And a lot of pretty much all digital logic is done with integrated circuits. Now this is a NAND gate, and inside here there's 3 transistors for the NAND gate, but there's actually a couple extra ones because they do some things to make sure that the voltage is all good and stable. But not only is there 1 NAND gate, there's actually 4 NAND gates on here, and we're only going to use 1, and you'll see that it works exactly the same way. So we have right now the output is on because these are 2 off, and if I turn either of these on, nothing changes. But if I turn them both on, it turns off, just like over here. So if we do the same thing, so we can do 1 on, nothing, 2 on, no change, both on, off. And digital electronics like this in integrated circuit form is what runs all our computers. So this one here probably has, maybe 20 or 30 transistors on it, but you look at your phone, the integrated circuits there have billions of transistors in them. And all they're doing is just turning things on and off.
As with our analog or linear chip, digital chips also have data sheets, and these data sheets are just as important. They tell us all sorts of important things. So this is the data sheet for the 7400, which is the chip we were actually using. And what it does a bunch of things. And there's more than just this in the data sheet, but this is kind of the important stuff. So this, of course, it's just like in the other data sheet, shows us the pin numbers and what's connected to which pin. So we have A and B are inputs, because if we look at it, we have a little function table over here, which tells us what logic stuff is going to happen. So we have A and B are inputs and Y is an output. So there's one gate inputs, one gate output. Our second gate inputs, second gate outputs. Then third gate inputs, fourth and output, and then fourth gate inputs and output. There's also some power pins, and we'll get to those in a moment. It'll show a logic diagram. This is the logic symbol for a NAND gate, and A and B are the inputs and Y is the output. And the nice thing about the function table or the truth table is it tells us what inputs cause what output. Now, H is the same as a 1 for a computer, and L is the same as a 0. And on these TTL 74000 series chips, H is also plus 5 volts, and L is ground or 0 volts. So whenever we drive one of these up to plus 5, we get a high, and whenever we drive it down to 0, we get a low. And the same with the outputs. When there's a low on the output, that means it's coming out as a 0 or 0 volts, and that's a 1 or 5 volts. Okay, so for this NAND gate, as we saw, if both inputs are high or 1, the output is a 0. If one of the inputs is a low, it doesn't matter. This X means it doesn't matter. That can be a low or a high, and we'll still get a high. Same thing here. If this one is a low, doesn't matter what this one is, because that could be a low or a high, and we get another high. And with these ones too, it's also important to remember that this here VCC has to go to plus 5 volts on this particular series of chips, and this has to go down to our ground or 0 volts, or a negative part of the battery. And the fact that this is this plus 5 volts, this is why we have to have a 5 volt regulator in our system. The circuit I was showing on the video, the power supply puts out 5 volts, but sometimes you don't have that, so you have to have some kind of voltage regulation so that you only have 5 volts running into this particular chip. Now, again, when you're going from schematic to the chip, chip is numbered just like the other one, so we have a little U or a dot sometimes, and that is pin 1. And then it numbers going up till we get on this particular chip to pin 7. Then the numbering continues on the other side, starting at the bottom, and then goes back up till we get to pin 14. On the 7400 series logics, the vast majority of them, the plus or VCC, right here, plus 5, is going to be whichever pin is immediately opposite pin 1, which on a 14-pin chip will be pin 14. And whichever pin is down at the bottom on the same side as pin 1, that's always going to be ground or negative. Now, when you're doing schematics, generally they will tell you which gate it is. So in this case, this is going to be the first gate, so pin 1, pin 2, and pin 3. So pin 1, pin 2, and pin 3. If this is the only gate used, you could technically use any of the 3 gates. They're all the same. But in this schematic, they want you to use pin 1, pin 2, and pin 3. What's important to note, in this schematic, there's actually a bit here that says that pin 14 goes to our plus 5, and pin 7 ground goes to our negative or ground. This may not be in the schematic. Sometimes this isn't there. Even if it's not there, pin 14 still has to go to plus 5, and pin 7 still has to go to ground. If if those aren't hooked up, this won't work. This is what powers the chip. So they need to be hooked up to plus positive 5 volts for power and ground for our minus. And again, this voltage value is for the 7474XX series of chips. There are some other types of digital logic called CMOS. They have different voltage levels. So again, that's what data sheets are for. But we're just going to be looking at this 7400 TTL series, this transistor logic. And remember that even when if they don't have this bit, remember that you still have to hook this and this up to positive 5 and ground.